Hi, welcome to lecture covering section 6.1, Exponential Functions. This is a new function that we have not discussed yet in this course. So this information might be new and fresh to you, and we're going to start in 6.1 by just looking at some general characteristics of the functions, and then we will move in 6.2 to look more closely at the graphs of these functions. So the first thing that we want to do in this section is just kind of understand what makes a function exponential and some of the manners in which those functions behave. So for us to gain a clear understanding of how an exponential function behaves, let us contrast exponential growth with linear growth. Now we're familiar with the linear function, and when we're talking about linear growth, we're talking about a linear function that has a positive slope on it. So we're going to construct two functions here in this XY table and compare them and see how they are different. So the first function that we're going to look at, f of x, this is an exponential function. Notice that the variable is in the exponent. So we're taking some set base, in this case, which is 2. And when we change our input value, it's actually the exponent that is changing. So if we contrast that with g of x, this being a linear function, we can see that we have our input that changes, but we're simply multiplying that by 2. So there's a difference in multiplying a value by 2 and raising 2 to a particular value. In the exponential function, we've got repeated multiplication that's happening there. So 2 times 2 times 2 times 2. However many times you've raised that base to 2. In the linear function, we've got repeated addition that's happening. 2 times some value says count that value twice, so add it to itself. So let's go ahead and fill in this chart to see how these functions differ from each other. And we'll just use -3, -2, -1, 0, 1, 2, and 3. Now, not necessary to use these particular values, but just nice, neat, right around the origin if we want to put them on the graph. So that's why I chose those. And let's start, since we're going to start with the exponential function, let's start with the positive exponent. So 2 raised to the first power is equal to 2. 2 squared is 4. 2 cubed is 2 times 2 times 2, which is 8. Don't forget that anything raised to the 0 power is just 1, unless that base is 0, and 0 to the 0 power is undefined. Now we have to remember some exponent rules here to address the negative exponent, so don't forget that whenever you have something raised to a negative exponent, if you change the position in the fraction, it creates a positive exponent. So 2 raised to the negative first power is just 1/2. 2 raised to the negative second power is the same thing as 1 over 2 squared, which is 1/4. And 2 raised to the negative third power is just, is equal to 1 over 2 cubed, which we know to be 1/8. Okay, so that's how this exponential function is behaving here. Now let's juxtapose that with the linear function. 2 times -3 is -6, so we're just doing 2 times negative 3 here. And so all of these are just going to be multiplied by 2. And we're multiplying by that changing input value. So 2 times negative 2 is negative 4. 2 times negative 1 is negative 2. 2 times 0 is 0. 2 times 1 is 2. 2 times 2 is 4. And 2 times 3 is 6. Okay, so earlier I said that multiplication is just repeated addition. So you can see we've added 2 each time we change our input value by 1. And I also said that an exponent represents repeated multiplication. So here we have our previous answer, if you will, being multiplied by 2 to get to the next one up. So we're multiplying by that base one more time to move up 1 in our input values. So exponential growth refers to the original value from the range that increases by the same multiplicative. In this case, that multiplicative is 2, the thing I'm multiplying by, over equal increments found in the domain. So notice I'm just moving up by 1 in my domain, but it's taking that and multiplying another time by 2 every time I move up 1 in my domain. On the other hand, linear growth refers to the original value from the range increasing by the same additive or number that I'm adding with over equal increments found in the domain. So apparently the difference between the same percentage, so the same percentage would be exponential here. And the same amount, which would be linear, is quite significant. For exponential growth over equal increments, constant Okay, I just realized I filled in the wrong words here. So although that does go with exponential growth, it's the next set of blanks here. This is over the same percentage. Now those words down there make sense. Over equal increments found in the domain, and linear growth. I'm trying to get my pen straight here. Sorry about the delay here. Sorry. Linear growth refers to the original value from the range that increases by the same amount. And in this case, that was 2. Over equal increments in the domain. So for exponential growth, we have a constant multiplicative rate of change. And in this case, it resulted in doubling our output every time. And for linear growth, we had a constant additive rate of change. Sorry about the blanks there. We'll move forward. Okay, so let's take a closer look. Once again, we have our exponential function. We now know that 2 to the negative third power is 1/8, 2 squared is 1/4, 2 to the negative first, 1/2, 2 to the 0, 1, 2 to the first 2, 2 squared 4, 2 cubed 8. Let's take a look at this on a graph. Okay, so we have negative 3, 1, 8. Let me get a different color here. I'll use blue. Negative 3, 1, 8. There's a little bit above the x-axis there. Negative 2, 1 fourth, a little bit higher. Negative 1, 1 half. 0, 1. That 0.01 is pretty important when we're talking about exponential functions. And we'll get into that a little bit later when we look at 6.2 material. 2 to the first power is 2. 2 squared is 4. 2 cubed is 8. So what happens here when we have exponential growth is that our number grows larger and larger very quickly. Now, let's think about the fact that there is a horizontal asymptote on the x-axis here. Let's say we had plugged in negative 100. And so we want to know what f of negative 100 is. So 2 to the negative 100th power is the same thing as 1 over 2 to the 100th power. It's a really, really, really big number on the bottom. But 1 is being divided by that. So it ends up being a very, very tiny, tiny number, but it's not actually 0. So that's why we have a horizontal asymptote on the x-axis, because unless we transform this function and shift it around in the plane, we're going to have a horizontal axis a horizontal asymptote of the x-axis, and actually we'd have to shift in the vertical direction to get a different horizontal axis. So you can see that the domain is negative infinity to positive infinity. For this particular function, the range is 0 to positive infinity. As x approaches positive infinity, our f of x values approach positive infinity as well. As x approaches negative infinity, here's our asymptote, f of x approaches 0. F of x is always increasing when it's in this form, and the graph of f of x will never touch the x-axis, and we just talked about y. So we have the horizontal asymptote y equals 0. And here's that important point I told you about. The y-intercept is 1. Okay, so just a general note about exponential functions. They come in the form of a times b to the x. X has to be a real number. A needs to be a non-zero real number. That's called the initial value. B has to be a positive real number, and it can't be 1. Because if B is 1, then it's really, really boring. Because 1 raised to any value is just 1, because you're just multiplying 1 over and over and over again by itself. So domain is all real numbers. We've already talked about the range. Range is all positive real numbers if A is greater than 0. So if your initial value is greater than 0, then your range is all positive real numbers. If A is less than 0, so if your initial value is less than 0, then the range is all negative real numbers. So this should give us a clue about reflection of this particular function, which we'll talk about in 6.2. The y-intercept is always 0a. So if we take a look at the function that we just put onto the graph, f of x equals, this is understood 1 times 2 to the x power. So if you remember, that graph went through the point 0, 1. It will always go through the point 0 and then whatever your initial value is, a. because whenever I raise 2 to the 0 power, which is when I'm plugging in 0 for x, that's just going to give me 1. So I'm going to multiply that 1. Let me write this out instead of just say it. If I plug in 0 for my x value, that's going to cause this whole thing right here to equal 1. So when I multiply 1 by my initial value, I'm just going to end up with my initial value. Okay, so which of the following equations represents an exponential function? Remember, the exponent has to live in, the variable has to live in the exponent. So this is not. And actually, you should recognize this as a quadratic function. We've already talked about these extensively. This second one, yes. We have A being 1, which is a non-zero real number, and we have B being a positive real number, 0.875, and our variables in the exponent. H of x? No. This is not an exponential function because our variable is not in the exponent. And J of x is yes. We have a positive real value for B, and my variable is in the exponent. Okay, so just a few things to jog your memory. Recall that the base of an exponential function must be a positive real number other than 1. Okay, so why does this have to be a positive value? Well, because if we have a negative value for B and we raise that to maybe a rational exponent, we could have the potential situation of getting a non-real number out. Why do we limit the base to positive values other than 1? We've already discussed this. 1 multiplied by itself is just 1. It doesn't matter how many times you multiply it by itself. And remember, the exponent is telling you how many times you're multiplying that base by itself. Okay, so our next tasks are to evaluate a rational function without using a calculator. So we're going to do a little bit of hand math here. So we want to evaluate this function at 2. So I'm just going to plug in 2 wherever I see x, so 2 plus 1. And this is 5 times 3 cubed. Now, you got to be careful with your order of operations. A lot of students are very tempted to multiply these, to multiply A and B together. And that is incorrect. Order of operations says I have to take care of this exponent before I can take care of any multiplication. So to correctly multiply these together, this is really 5 times 3 cubed. 3 cubed is not 9. You're not multiplying 3 times 3. This says multiply 3 by itself 3 times. 3 times 3 times 3 is 27. And 5 times 27 is 135. Okay, here we want to also look at f of 3. So we have an a value of 8, a b value of 1.2, and then 3 minus 5. Okay, so this is 8 times 1.2 raised to the negative second power, which is the same thing as 8 times 1 over 1.2 squared. And let's see, 1.2 squared is 1.44. So this is 8 times 1 over 1.44. This is really an 8 over 1 times a 1 over 1.44. So this is the same thing as 8 over 1.44. So I can do the division, and we are told to round to 4 decimal places. So when I divide 8 by 1.44, I get 5.555555555, And so that rounds to, so I need to use the approximation symbol, 5.5556. Okay, so I just brought this information over here. General note about exponential growth. Grows by a rate proportional to the amount present for any real number x, positive real numbers a and b, where b is not 1. We always have this form for an exponential function. A is known as the initial or starting value. B is the growth factor or growth multiplier. So this is just cluing you into some language that is used in word problems having to do with exponential growth. Exponential growth is going to be very important to you scientists, you statisticians, anybody that's doing research really, populations, things like that, needs to know about exponential growth and decay. Oh, chemists really need to get used to working with this. Okay, so at the beginning of this section, we learned that the population of India, well, we didn't in our little lesson here, but in your book you do. Population of India is about 1.25 billion in the year 2013, with an annual growth rate of about 1.2%. The function that mirrors this situation, so P of t is the population based on time t, is 1.25 times 1.012 raised to the t power, where t is the number of years since 2013. So notice we have our initial value of 1.25 billion, and we have our growth factor of 1.2% right here. That's how I'd write 1.2%. We have the extra 1 because we have to account for that first 1.25 billion that we start with. So this is basically 100% of that 1.25 billion, and then I'm adding on that 1.2% that I gain every year. So that's why the growth factor is 1.012. So to the nearest thousandth, what will the population be in 2031? Well, we need to know how many years have occurred since 2013 up to 2031. So the first thing I'm going to do is subtract these two values to find their difference. So 2031 minus 2013, let's see, 2031 minus 2013 is 18. So I'm going to, if I want to find the population in 2031, I want to plug in 18. Just getting a different color here. 18. Wherever I see t in this population function. Because it's been 18 years since 2013 if I'm looking at 2031. So I've got my initial 1.25 billion, and I multiply that by my growth factor of 1.2% raised to the 18th power. So the first thing I need to do, order of operations wise, is this 1.012 raised to the 18th power. So 1.012 raised to the 18th, I'm just putting this into my calculator. I get a really nasty number. It's an irrational. It's 1.2395076. I don't want to mess with that number in my calculator. I don't want to round it off before I multiply by the 1.25. That creates round off error. So what you want to do is just leave that value in your calculator and multiply it by 1.25. I'll show you real quick on my calculator. I haven't turned my video on in a long time. Hi. For those of you watching this on the Blackboard Collaborate player, you should be able to see this. If you're watching this in MP4, it will not show my window, but there's my 1.012 raised to the 18th power. And it's that long, nasty number, 1.239507689. And all I'm going to do from there, I'm not gonna erase that out or round it off or anything. I'm just gonna hit multiply. And you see it says answer and then star. That's saying it's multiplying my last answer that I got. And then I'm just going to multiply that by 1.25. Okay, I'm turning my camera off. I have to keep my camera off or my tablet won't work properly. Okay, so when I multiply those numbers together, I end up getting 1.549384611, and it says to round to the nearest thousandth. That is the third place after the decimal. So I'm rounding to this place. I look next door and I see a 3, and that says to leave it as it is. So this is equal to 1.549 billion people. Okay, so what this says is in 2031, it is predicted that there will be 1.549 billion people in India. If you want a better idea of what that number is, that's 1,549,000,000. Okay, so the population of China was about 1.39 billion in the year 2013. It's an annual growth rate of 6%. So here we see our initial value showing up in our function, and here we see our 6%. Oh, 0.6%. Okay, that makes sense as to why there are three places behind the decimal. We had to have the 1 there to account for that 1.39 billion that we started with. So we're doing the same thing here. Figure out how many people we expect to have in China in the year 2031. Well, we know that our T will be equal to 18 because 2031 is 18 years since 2013. So P of 18 for China, we have our initial population of 1.39. We're growing at 0.6% every year. And I'm just going to put this all into my calculator. 1.006 raised to the 18th power gives me 1.113688289, and then I'm going to multiply that value by 1.39, and I get my population in 2031 in China 548026722. So the population is approximately 1.548 billion. And then it says, okay, contrast this or compare this to the population prediction in India. So let's go back and grab our population prediction for India, and I'll take it to this other page so we can look at them side by side. Okay, so let me just label this. Okay, this is India. and this is China, notice that China started with a bigger population than India did in 2013. But India's population is rising quicker than China's population is. So actually, in India, we end up with a larger population in 2031 than we do in China, which is crazy, but interesting. Okay, so finding equations of exponential functions, and hopefully you've picked up on the things that I've pointed out to you about where particular information goes in the exponential function. So if you're given two data points, this is how you write an exponential function. If one of the data points has the form 0a, then a is your initial value. You're rarely going to be given that information, but it's nice if you are, and it's nice to know that if you are, what you can do with it. Then you would substitute your second point for x and y, or x and f of x, and then solve for b to write your equation. If neither of the data points is your initial value, or your y-intercept, basically, then you're going to substitute both points into the equations with the form a times b to the x, and solve the resulting system of two equations and two unknowns to find a and b. Using the a and b found in the steps above, you write the exponential function in the form a times b raised to the x power. Okay, so we're actually going to be kind of clever with our problem that we've been given here, and we're going to force our information to have a y-intercept, to be given a y-intercept, so we'll have that initial value. Let's take a look at this wolf problem here. So wolf population is growing exponentially. That tells us that we can use this form here to write the equation for this situation, or write the function for it. In 2011, there were 129 wolves counted. By 2013, the population had reached 236 wolves. So what we can do, we can force our first counting of the wolves, which was in 2011, we can force that to be year 0. And we counted 129 wolves. And then we have our 2013 data as being 2 years since 2011, and we counted 236 wolves. So what 2 points can be used to derive the exponential equation model in this situation? The points 0, 129, and 2, 236. That says write the equation. So we have our initial value, we forced our initial value to be 129. So far, I know that f of x is equal to my initial value 129 times some b value raised to the, let me use the notation that they told us to use. They told us to use n and t. So n of t is our function, so we're raising some b value to the t power. T is equal to years since 2011. That's how we set it up. So I already have information that I can plug in for t and n of t And then I can use that to solve for b. So I'm going to plug in for t and n of t, and I'm going to use that information to solve for b so that I can write my function. All right, so I have 236 is equal to 129 times b raised to the second power, so squared. And now I just need to solve for b. So the first thing I want to do is isolate my exponential function by dividing both sides by 129. And I'm just going to leave that as the fraction 236 over 129. I don't want to work with that fraction. I don't want to reduce it because I'm going to take the square root of it in a moment anyway and put it into my calculator. So I'm just going to leave it that way so I get the most precise answer. Take the square root of both sides. I do not need to consider the negative square root because we're talking about a population of wolves and there's no such thing as a negative population of something. So I'm just going to put into my calculator the square root of 236 divided by 129. And when I do that, I get approximately, and let's see what it says to approximate to. Right, the equation representing the population. It doesn't tell us, so we'll just round to the nearest whole number since we're talking about wolves and we don't want partial wolves here. So I am getting a b value of 1.35. Okay, so my function is now I know that my function is n of t equal to 129 times 1.35 raised to the t power. So if I wanted to say, okay, what is the population of the wolves going to be in 2020? Well, let's do that. What about the year 2020? Well, that would give me an n value of 9 because that's 9 years, I'm sorry, a t value of 9 because that's 9 years since 2011. So let me get my pen here. That is a t value of 9. So n of 9 equal to 129 times 1.35 to the 9th power, and I'm just going to put that into my calculator, 1.35 raised to the 9th power, and then I'm going to multiply that by 129, and I get in 2020, my population will be approximately, I'm going to round to the nearest whole wolf, 1,921 wolves, 9 years later. Okay, so here we have not addressed systems of equations in this course, so I'm skipping this problem because you have to know how to do systems of equations to work through these, and I will go and modify your homework so that these are not addressed. Sorry, I just realized that. Okay, so given the graph of an exponential function, try to write its equation from there. All right, so we definitely need to have the y-intercept, which this one's nice and neat, the 0.03, remember? That gives us our initial value, A. Okay? And then we can choose one other point so that we can find the equation. And it looks like it goes through the point 212. Okay, so we have our general form, f of x equals a times b raised to the x power. I know that my initial value is 3, and I have one other point that I can plug in for x and f of x. Here's x, and here's f of x. So 12 and 2. And I'm going to solve for my b value. So I'm going to first divide both sides by 3 to isolate the exponential expression. And I get 4 is equal to b squared. Take the square root of both sides. B is equal to 2. Once again, I don't have to consider the negative value because b's got to be positive. That's part of the characteristics of the exponential function is that b is positive and it's not 1. So here b is 2, so now I'm ready to write the equation of my function here, f of x equal to, have my initial value 3, and then this is times 2 to the x power. Okay, so here is one way of using your graphing calculator to find an exponential equation that includes these 2 points. So I'm walking through this myself on my TI-84. Unfortunately, Desmos doesn't give us the ability to do this type of thing. So I'm just going to walk through this step by step, and hopefully you have your graphing calculator there as well. So we could actually go back and do that question we just skipped without having to know how to work through systems of equations. All right, so the first step is to press the stop button. And then you're going to, it doesn't tell you, but you're going to push enter where it says edit. So you have to go down to under the stats list, the first one, edit, and then push enter. And if you have anything sitting in your L1 or L2, these are lists, that's list 1 and list 2, you got to clear it out. So I am going through and clearing my lists by, oh, I thought I was clearing my list. Oh, I'm sorry. Don't edit and enter. What you need to do is, let me delete this. Can you tell I don't use my calculator that much? Not for this type of thing, at least. I do everything by hand. You're going to arrow down once you hit stop to clear, well, it's a CLR list. Okay, so I'm going to arrow down and clear my list. Okay, now let me go back and see if that actually happened. I'm not sure that it did. It didn't. Dang it. Let's see, I can't, it's not clearing out for me. Let's see if delete will work. Delete won't work either. I don't have, let's see, enter the x coordinates given. Let me see if I can just zero it out. So I'm going to go down to edit list 1, and I have an x value of 3. Okay, let me do that. And I hit enter, and then my next x value is 6, and I still have some values. So let me see if I can, okay, now it's letting me delete. I just had to start the list there. Okay, I'm having to clear all my lists now. I'm doing it with the delete key actually. Okay, so for my x value of 3, in my list 2 I have 75.98, and I hit enter, and then it moves down to 6, and I have 481.07, and I hit enter. Okay, so I've got my list 1 and my list 2 ready to go, and I'll just click on my video real quick to show you what that looks like. Okay, so you can see I have my list 1 and my list 2. All right, and then from there, it says to press stat again, so I did that. Cursor to the right to calculate, so that's your next list menu under stat. And then scroll down to exponential regression. What this is going to, and that's actually value 0 all the way down at number 10, exponential regression. And then hit enter. It's going to take those 2 points and calculate for you. Okay, and let me show you what you get. Actually, I'm going to write it on the screen in case you can't see it. It tells me, okay, it's giving me this function in the form of y equals a times b raised to the x power. So it's telling me, it's giving me an exponential function. It tells me my initial value is 12.000250028. It tells me my b value is 1.84999197. Don't worry about r squared and r. Those are for statistical purposes. Those are your correlation coefficients. So from my calculator, I know that I can write the equation f of x equals 12.0003, it rounds up, times 1.84. We'll cut that off at the hundredth place there. I don't have to. We'll do 1.85 raised to the x power. So let's actually go back and use the same technique. Instead of using systems of equations, go back to stat and then do edit. Move over to edit list 1, and those are our x values. So I'm going to enter 1, and then I'm going to enter 2, and then I'm going to arrow over to list 2, and next to the 1 I'm going to put 3 for my y value and enter, and then 4.5 and enter. And then I'm going to do stat, calculate, and I'm going to go all the way down to exponential regression. And here's what I end up getting. First, it tells me it's giving me an exponential function or information for the exponential function. And it says a is equal to 2, b is equal to 1.5. So that function is f of x equals 2 times 1.5 to the x power. It's nice to have a powerful calculator that does that for you so you don't have to use systems of equations. These systems would not be fun because you've got the variable and the exponent. Okay, so one of the last concepts in this particular section has to do with interest, and we're talking about interest on accounts. So, and compound interest to be precise. Saving instruments in which earnings are continually reinvested, such as mutual funds and retirement accounts, use compound interest. Just so you know, it doesn't have to be a savings account. It can be a loan. Loans use compound interest as well. So whether the money is owed to you or you owe the money, compound interest is going to come into play here. The term compounding refers to interest earned not only on the original value, but on the accumulated value of the account. So for example, let's say I deposit, and this is going to be an extremely non-real world situation. Let's say I have a savings account that pays me 10% interest per month, which is just ridiculous to even think about, but the numbers are simple to work with. So let's say at the beginning of the first month, I deposit $100 into that account. So at the end of the first month, at the beginning, I deposit $100 into that account. And at the end of the month, I'm given 10% of the amount that sat in the account. So 10% of 100 is 10. So at the end of the first month, I have $110. The second month, I start with that $110. I take 10% of that, which is $11, and add it to it. So at the end of that month, I have $121. That's compounding interest. So you're not only gaining interest on the original amount or principal that you deposited into the account or you took out as a loan, but you're gaining interest on the ending balance for each compounding period. So we have different compounding periods, and I'll lay them out for you on the next page. You can have things that are compounded monthly, you can have daily, you can have annually, biannually. So these are all different compounding periods. So when we're wanting to calculate the compound interest, we use what we call the compound interest formula. And here it is right here. And what this says is the account value, A of t, measured in years. T is measured in years, so there's T right there. That account value is equal to my principal, or what I started with. Sometimes it's referred to as the present value. And that's multiplied by 1 plus my rate that I'm given, R, and you'll need to convert your rate to a decimal. So like if you have 5%, you don't put 5% in, you put 0.05 in. And you write percents just like you would money. So 5% is written like 5 cents. That's why when we had 1.2% in another problem, that was written as like, that'd be like 1.2 cents, so 0.012. So your rate written as a decimal divided by your number of compounding periods per year raised to your number of compounding periods per year times your time in years. So this is called the compound interest formula. Okay, so here are your different compounding periods, and this isn't all of the compounding periods that you can have. These are just some. Annually, because the compounding period is figured by how many times it happens per year, that would be 1. Semi-annually, that's twice a year, so 2. Quarterly is 4. Monthly, we have 12 months in a year, so 12. Weekly, 52. Daily, now here's something to notice. Daily is 360. So even though we have 365 days in the year, the banking sector uses 360 as the compounding periods for something that compounds daily. Okay, so if we have an initial investment, let me color code this again. P is our principal, and we have our accumulated value, We have our rate and our compounding periods, and that is multiplied by our time in years. Okay, so we have an initial investment of $100,000. That's our principal. At a rate of 12%, that's written as 0.12, compounded weekly. That means N is equal to 52. What will the investment be worth? So what is our accumulated value for a T of 30 years? So we just plug everything in. Our accumulated value is equal to our principal, 100,000, times 1 plus our rate, 0.12, divided by 52, raised to the 52 times 30. And I just put all this into my calculator. I'm very careful when I do it, using parentheses where I need to. So let me put this in, and then I'll write on the screen how I put this into my calculator. So 100,000 times 1 plus, I'm going to use an extra set of parentheses to hold this fraction together, 0.12 divided by 52. When in doubt, use parentheses. I'm parentheses happy. And then I'm going to raise that to the parentheses 52 times 30. Okay, so this is how I just put this into my calculator. I did 100,000 times 1 plus, and then I held this in parentheses, 0.12 divided by 52, in that inner parenthesis, in the outer parenthesis, and then I raised that to 52 times 30, into parentheses. And when I put that into my calculator, I get that at the end of 30 years, this account will be worth $3,300,000, 3,644,675.88, and I rounded that to the nearest penny. Okay, so another compound interest problem here. A 529 plan is a college savings plan that allows relatives to invest money to pay for a child's future college tuition. The account grows tax-free. That's nice. Lily wants to set up a 529 account for her new granddaughter and wants it to grow to 40,000. Okay, so this is what she wants the accumulated value to be. Over 18 years, she believes that the account will earn 6% compounded semi-annually. To the nearest dollar, how much will Lily need to invest? So what we're actually going to be solving for is our principal. How much does she need to invest to begin with to end up with $40,000 18 years later? Well, let's just plug everything in. We want to end up with $40,000, and we don't know our principal, times 1 plus our rate divided by our compounding period, and that's raised to our compounding period times our time in years. Okay, so we have 40,000 equals P times, okay, so 1 plus, I'm going to go ahead and simplify in the parentheses there. 1 plus 0.06 divided by 2 is 1.03. And that's raised to the 2 times 18, which is 36. Okay, so I need to divide that factor of 1.03 raised to the 36th power off of both sides to get what I need to invest as principal. Okay, so 40,000 divided by 1.03 raised to the 36th. And I get that she needs to invest, and it says round to the nearest dollar, she needs to invest $13,801 so that 18 years later, her granddaughter will probably not even have enough to pay for her first year of school, especially in today's world. $40,000 is not much money when it comes to paying for college. All right. Okay, so this is the last concept that we have here with exponential functions. And that is the idea that, okay, so we talked about compounding periods, and you can see here we have annually, semi-annually, and all that. Well, there is also a thing called compounding continuously. It's compounding at the rate of 1/trillionth of a second. So every trillionth of a second, it's recompounding itself. So what happens in this situation is that our n value, our compounding periods, begin to approach infinity. So we can see what the difference is. Okay, so we have a rate of 100% compounded annually in this first column here for 1 year, and then compounded for 1 year with 2 compounding periods. So that comes to 225. And then 4 compounding periods, we end up with 244, and so on and so on. Notice these last 4, really last 3 values. We get to once per second for a year. So apparently there are, let's see, 31,557,600 seconds in a year. So this compounding every second. Notice these last 3 values are all starting with 2.7182. 2.7182. So what we discover is that the closer our n value approaches infinity, the closer this entire expression, I drew through it. Just move it. There we go. The closer that this entire expression, 1 plus 1 over n to the n, gets to this value, 2.718282. We name this value E. So you have probably wondered what that funny looking E is on your calculator. This is known as the natural base. And it's actually an expression that, well, it's a value, 2.71828, that this expression is approaching as n, or the compounding periods, what they say increases without bound, and that means it's approaching infinity. So the higher that number n goes, the closer that expression will evaluate to 2.71828. So we have to know this because we have these situations in interest problems where we do have things that compound continuously. Like your credit cards compound continuously. Congratulations if you just discovered that for the first time. All right, so let's just work with our calculator for a moment just to make sure that you can put these in correctly. If you'll notice, the E button is the second function for your LN button. So you have to push the blue second key at the top of your calculator and then push LN. And when you do that, you'll get, on your calculator, it will show E, and it'll raise it to, and then it'll open a parenthesis. It wants you to tell what to raise that E value to. So to evaluate E to the 3.14 power, it says round it to 5 decimal places. On my calculator, I push second, the very top left, and then I push LN, and that on my screen does E raised to the, and I'm going to type in 3.14 and close that parenthesis. And when I evaluate E to the 3.14, I get 23.10386686. We were asked to round to the 5th decimal place, 1, 2, 3, 4, 5. I look next door, that's going to round up. So I get 23.10387. We can also raise E to a negative value. So when I put E raised to the negative 0.5 into my calculator, E raised to the negative 0.5, I get that E is approximately 0.60653, and that is rounded. Okay, finally, how is this useful to me? Well, we have what we call, and I'm going to draw it bigger, the PERT formula. In our original compounded interest formula, A of t was equal to P times 1 plus R over N to the NT. Well, when our N value approaches infinity, it changes all of this. There's an understood 1 in front of the R multiplying. 1 plus 1 over N to the N, that's E. So what it changes into when we compound continuously is what we call the PERT formula. A of t equals P times E raised to the RT. Okay, so P is our principal, R is our rate, and T is the period or term of the investment, how long you've invested. Okay, so a person invests $100,000 at 12% interest rate compounded continuously. What will be the value in 30 years? So A of t, in this case, since we're compounding continuously, P times E raised to the RT. My principal is 100,000, and I'm going to multiply that by E raised to the, and I'm just writing this how I'm going to put it into my calculator, 0.12 times 30. And when I put that into my calculator, 100,000 times E raised to the 0.12 times 30, I get the value of my investment as 3659823. I'm going to round to the cent, 44. So that is $3,659,823.44. Radon decays at a continuous rate of 17.3% per day. How much will 100 milligrams of radon-222 decay to in 3 days. So we still want to know what our accumulated value is. So this is a problem that has nothing to do with money, but we can use the same PERT formula because we're told it decays at a continuous rate. Now it decays, so we're not growing. So we need a negative rate because we're depleting. We start out with 100 milligrams, and we multiply that by E raised to the, okay, so 17.3% is this is an R of negative, because it's decay, negative 0.173. So negative 0.173 times, our time in this case is given in days. So 3 compounding periods basically, because it decays per day. So the time in years only applies to our investment function there. All right, so when I put this into my calculator, 100 times E raised to the negative 0.173 times 3. After 3 days, this radon-222 will decay to 59.51 milligrams, and that's approximate, that's rounded. That's all I have for you. I hope this was helpful for you to understand how to work with exponential functions with growth and decay.